Welcome to the optical communication course. Today we will see that a optical receiver operation. Now, what do we mean by this optical receiver? So basically, we have seen that earlier we have a link, that optical link. We say that light propagating or light emitting from the source, either it can be a LED source or a laser source. It will fall on the detector. Okay. Now this one is about your source, and this one is about a detector. Now this one source is what? It can be a light emitting diode or laser. It emits a photon of light. Then light will propagating through this fiber. We have the core fiber and a cladding here layer. That light is propagating through the fiber, and then light coming from this fiber from this end, and then that light will falls on the detector. Now, when light falls on the detector, it will penetrate in that junction, PN junction or a PIN, whichever the material we are using, avalanche photodiode or a PIN diode we are using. That photon of energy enters in that detector, then according to that, it generates the electron and hole pair. So means we say that each photon will generate a electron hole pair. If it is a PIN diode, so each photon of it will generate electron hole pair. Because of that generation of the electron hole pair, the current will produce, and that current we will say that that particular current is a photon, okay, photodiode current or photodetector current. Now, in the case of avalanche photodiode, so now a single photon generates a multiple electron hole pair. That is a multiplication process in avalanche photodiode. In that case, the current is different. Now, what type of a detector we are using, detector device we are using, according to that, we'll get the current here. Now, the topic we say a optical receiver operation. So, optical receiver operation, it consists of what? Whatever the receiver we say, it consists of a photodetector, then it has an amplifier, and then it has a signal processing circuitry. Now that is about the a optical receiver operation. If you see here, so we have a choice of a detector. We consider the detector. It will generate the current because that length of this link is a too long. So that's why that energy level, or we can say that a photon of energy is reduced now because of that length. So that's why we need to amplify whichever the signal we have received here. So that's why we require a amplifier. So whether we have to amplify the light or whether we have to amplify the detected signal, that is it. There are the various types of amplifier. We'll see in detail. And then a signal processing circuit. And in a signal processing circuit, we require a understanding of that information. So means what? The receiver role is what? It converts that optical energy from the end of a optical fiber into an electrical signal, and then it will amplify that signal to a large enough level so that it can be processed by this signal processing circuitry, and we will get that information. If you see that there is an input that is about a current pulse, and that current pulse is about the information that we can say that it is in the form of 1010 format, and according to that we'll should get that 1010 output. Now that is about a receiver operation. Now before under going in detail of a receiver operation, we'll see that a fundamental of a receiver operation, and before pointing out towards this fundamental of receiver operation, we'll see that how your optical data link transmitted. Now we consider here a signal path through an optical data link. Now in general, if you see that we have the electric input pulses, and that electric input pulses have the format of bit format is about, we can say, 1 0 1 here, and that pulses are the input to the your source, and that source can be what, a LED, or we can say that a laser, and that will, we can say that, act as a transmitter there. And from that optical source, it produces a optical power pulses. Produces a optical power pulses, and this is about your optical power pulses. If you see that a duration for this one is a TB, similarly the duration will be same, that will be a TBR. And then we use a optical fiber for transmitting this particular signal. When we have the optical fiber, at the end, that pulses will be attenuated, and that will be distorted. That attenuated and distorted optical power pulses. Now if you see that the transition here, we say it is about 1, then a 0, then a 1. Similarly transitions for 1 0 1 here. Similarly transition for 1 0 1. Now that's about a spreading of a pulse takes place here, and then that will be the input to the detector, and that detector can be a pin detector, or we can say that a avalanche photo detector. And then after that we'll get that a electric current pulses, and that electric pulse contains detector noise. And then we require a amplifier to amplify your signal and we require a filter to remove the noise. And after that, we'll get that a voltage pulses and and a amplifier noise. And then we require a decision circuit, and pulse generator here, and then it produces that whatever the expected output in the form of 101. So we'll receive that information that is about a 101, that is about a regenerated output voltage pulse. And then we have a signal processing equipment, and according to that your transmission will be takes place. Now if you see that the overall case here, we have the input pulse, input current pulse, and if you see that that transmitted signal have the labels of a 010 format, that is about it binary, in the form of binary, and a duration is about a TB, we say TB duration there, and that is nothing but a bit period. Now then, a principle of information, whatever the data information, how we are sending the information, that is in a binary format, or what technique we are using for this sending the data in a digital format. So it can be of amplitude shift keying or a on off keying, where we can say that the voltage level will be switched from the higher level to the lower level there. So that is about the case we can use the technique, and the output will be in the form of a 1 and 0, and then that is about the electric pulses that will be propagating through these, or that will be the input to your source there. And then a source that will convert in the form of a current, your output will be in the form of a current, will get that whatever the electric input pulses we have according that a electron and hole pair bonded here, and so that a photon of energy is generated. So now that is nothing but a light, and that is, we can say, that is about a optical power. So we'll get that a pulse, that output in the form of a photon of energy, and then that will be propagating through the fiber, and that photon of energy that will be attenuated or distorted, we say, and then that is nothing but what we can say a dispersion here. And then we have a detector, light will falls on the detector, it will generate the a current, means it will, each photon will generate, we say that earlier, or when light falls on the detector, each photon will generate a electron and hole pair in the case of a pin diode. In the case of avalanche photodiode, so there will be multiple electrons and hole pairs are generated, and then that generation of that electron hole pair, that electrons will move to your and means motion of that electrons and hole from conduction band and a what we can say that valence band. Okay, so according to that, there will be a generation of a current. Now that is about electric current pulses, and that electric current pulses means we are getting a current pulses from this photon of energy, and that electric pulse contains the detector noise. Now, what are the various detector noise? We'll see one by one. Because the detector it has a generation of that a photon, sorry, generation of that electron and hole pair because of that photon. So that's why that process of generation of that electron and hole pair, that process is a statistical process. And if you see the distribution of that process, that it will be a Poisson distribution, and we can say that the noise, we can say that a short noise or a Poisson noise. And again, because of that photon, it will generate a current. But if supposed to be there is no input to this detector, there is no light. Even in without light, the detector generates some particular current, and that current is called as a dark current. And because of the dark current, there will be a noise that is called as a dark noise. We'll see in detail. And the dark noises have two types. That dark noise, because we have a detector, and if you consider the detector, because a photon will be inserted inside this particular detector, and according to that electron hole pair generated, and will get that response of a current. Now, because of a photon, current will be generated. But in the case of a dark noise, external no input is there. Means if you consider that your device is placed in a dark room, but even if it is placed in a dark room, it generates some particular current, and that current is called as a dark current. So inside the material, current is generated, that is called as a bulk dark current. And on the surface of this material, if that current is generated, that is a surface dark. Then after the detector, we use generally a load resistance. And if you consider that a power output, that will be approximately depending upon that a load resistance. Now, because of a variation in the temperature or a thermal variation, so what will happen? That noise will generated, and that noise is called as a thermal noise. So that is about your a noise, and after that we produce that gives the output to the amplifier and filter, and then we have the amplified output and noise. For noise we require a filter here, so noise will be removed, so we'll get that output. But that output have a noise. That noise is from the amplifier. The detector noise, everything noise is removed, but there is a noise that will be from the amplifier. Now then a decision circuitry we require. Why decision circuitry require? Because we need to make that decision regarding whether that information is 1 or is 0. So means 1 and 0 means what? Because the output come from this detector, that will be amplified, and that will be passed through this filter, when it is passed through the filter, that it will reduces the noise. And then we have this received signal. There may be a what we can say that a intersymbol interference occurs because of a pulses overlap. So that's why we need to see that whether we are getting that overlap pulses or whether we are getting that 1 or 0, because we say that 1 and 0 some label is there. For 1 we say that that is some voltage level, and for 0 there will be some label. So means in the case, suppose we say that output is about a 1 level and this is about a 0 level. So means when we are receiving the signal, if it belongs to this particular region, you can say that is about a 0 level. If it is belongs to this particular one, then we can say it is 1. So that's why we need to mention some particular value, threshold value. So above the threshold value, we should say that it will be 1, and below that threshold value, it will be a 0. So that's why the decision circuitry that will tell you whether that information will be a 1 or a 0. And then we can say that a signal proceed. Now in this optical receiver operation, we will see here what are the various noise present and how this noise come, and then various amplifier and a filter required, and what are this decision circuitry we require, that we will see one by one. So now we go to learn about for the given particular detector, we say that what are the various noise present, and then what will happen to the signal to noise ratio. So generally if you see that that is about a photo detector noise, and why this noise will become, because there is a weak signal will be detected by your detector, and sometimes when we say that whatever the weak signal detected by the detector, so it contains the information or it doesn't contain the information. If it doesn't contain the information but again it will be detected by the detector, so then that belongs to the noise there. So now for this noise we should define that what will be the signal to noise ratio. So signal to noise ratio means what? That will be a signal power from a photo current divided by photo detector noise power plus amplifier noise power. Now this one is nothing but a signal to noise ratio, because generally we say that for the detector requirement, so responsivity, that term we say that earlier, responsivity term for a given particular photon of energy, how your detector will work, that is nothing but a responsivity. So means for even if for this low level of a photon or low level of a optical signal, that will be detected by the detector. So that's why we say that a sensitivity and this particular responsivity term for this detector. So means weakest signal will be detected by the detector. So that's why your output of the receiver that should maintain that a particular signal to noise ratio. So that noise, that can be noise from the a photo detector as well as the noise from the amplifier. So output we say here we have a output we are getting from the detector as well as a amplifier here. So that's why noise will be a part of this particular receiver reception process. So signal to noise ratio, signal power from the photocurrent with respect to whatever the noise we have. So generally we say that a noise in a photo detector that will be resulting from the statistical nature. And that is a statistical nature of what? A photon to electron conversion. Because what happened here? That is photon will generate a electron hole pair. That's why I can say that photon to electron conversion, and that is a sources of a noise and a thermal noise that will be associated with that amplifier circuit. To get that higher signal to noise ratio or to achieve the higher signal to noise ratio, so then a photo detector that have a high quantum efficiency. Okay, high quantum efficiency. So what do you mean by this quantum efficiency? Quantum efficiency means what? A generation of a electron hole pair for the given particular photon. So when we get the high quantum efficiency, when we have the generation of that electron and hole from this particular photon of energy. When this detector have the high quantum efficiency, then it will generate the large power. Okay, detector should have a high quantum efficiency to generate large power. And another condition is what? Whatever the noise present in the photo detector, photo detector noise, because we say photo detector noise and the amplifier noise, that should be low. So now simple. Now these are the two conditions we say that for the photo detector to improve the signal to noise ratio. One is about the high quantum efficiency, another is about a noise. Now if you see here, the equation, signal to noise ratio. Signal power from the photocurrent means photocurrent. If we say that this word a photocurrent, how this photocurrent generated that IP? Because of that electron. Electron will flow through this detector. Means electron will flow through. How it will flow through? Because photon will generate the electron hole pair, so that's why it will generate that current. So signal power from the photocurrent. If when this photocurrent will be large, if there will be large number of electron hole pair generation, then photocurrent will be large. When this will be large number of photon and electron hole pair generated, when we have the high quantum effect. So that's why the high quantum efficiency that will generate a large power. Then another if this will be large, so this quantity should be low. So that is about a noise. Noise from what? A detector and noise from this amplifier. If this quantity is low, so naturally signal to noise ratio will be large. So now this is about a condition here to get that high signal to noise ratio. But in the case of a detector, so generally what? So it will detect the minimum signal, minimum optical power level that will be detected by the detector. So that's why that noise will be generated because of that property of a detector to detect the minimum optical power level. So that's why there will be a noise generated, and for the detector we say that a sensitivity word, and that sensitivity we can say that it will detect that a minimum detectable output power, minimum detectable output power, and that will be the sensitivity. So means it will generate the a photo current. So that's why the optical power will produces that a photo current, even if we say that is about a minimum detectable, and if it is a minimum, so that we can say that is a part of a noise, suppose. So in that case, that magnitude of that particular current, that will be a root mean square of the total noise current. So we can write that a current in terms of what? A root mean square. Suppose we say that a current, likewise we can write in the form of root mean square here, current. So now we can see that what are the various noise sources in the detector when we consider that a receiver operation. Now generally if you see that a photodiode, a photodiode has a noise sources, and that noise sources are a quantum noise on a dark current noise. These are the two noise. One is about a quantum noise and a dark current noise. And this dark current noise that is generated in the material, or we can say that it will generate in the bulk material. So that's why we have the bulk dark current noise, and another noise we can say that it will generate on the surface leakage current, due to surface leakage current. So that's why you can say that a dark surface current. This quantum noise, we can say it is about a short noise. That short noise we can express I square short. This one is about a dark bulk current. We can express that dark bulk current, and then we can express that a surface current, that is about I d s. Okay. Now all this current, if you see here, they have some values that will be depending upon that a photon of a current. So now we will see one by one a quantum noise or a short noise, and this short noise that will be arises from the statistical nature of the production and a collection of a photoelectron. That is, we can say that it is about a statistical nature. That will be a statistical nature of generation of a photoelectron. Okay, statistical nature for the generation of electrons. When it will generate, when there will be a optical signal will be fall on this detector. Okay, so now just like a detector we have, this is a detector. Now this is about a photon. When this photon will fall on this particular detector, it will penetrate inside the detector, and then electron and hole pair generation started, and then we'll get that a current that is called as IP. That is about a photon current, and that photon current, if you consider that the value of this photon current, it is depending upon that what will be the modulation index, or we can say that what will be your input to this detector, and then what will be the, we can say that equivalent circuit. In the equivalent circuit, what are the various components in the detector there. So now if you see the equivalent circuit of this detector, it has a capacitance. So I'll just draw here equivalent circuit of a detector. We can say that this is about a capacitance CD here, then a resistor RS, then a load resistor RL, then we have a RA here, then we have CA, and then we have the amplifier. Generally, how your detector works, we have mentioned earlier, that is bias voltage. This one is about a RL, okay, and then we have the amplifier. This is about a circuit, and this is about a equivalent circuit. This one is about a photodiode. This one is about a main circuit. We can say that a photodetector at a receiver, and then this one is about a equivalent circuit. And this equivalent circuit, if you see that it has a series resistance, that is about a RS. Then we have a junction capacitance, or we can say that a packaging capacitance. Then we have a load resistor, that is about load resistance here. We say load resistor here. Same, we have a load resistor here, and then this portion is about your a amplifier component, that is about the input capacitance and the resistance there for this amplifier. So that is about the equivalent. Now then it will generate, we say that is about a photon of a current, and that photon of current depending upon that how it will fall that photon will fall on this particular detector there. Then a current is generated, and that current is generated. It is depending upon that optical power, and we have this a quantity of a photon generation that will be depending upon that eta q hv. Hv is about the band of energy, q is about your charges here, and this is about the quantum efficiency. So that is about your current. This is about your optical power. So optical power at that particular instant t, suppose. So that's why we will get that current at that particular instant t. So based on this quantum efficiency, we'll get that a input current eta q p of t. So now I'll redraw here. I'll rewrite again. Sorry, is nothing but what a quantum efficiency and a photon of energy hv, and that is about the optical power. Okay. So now that eta is about a quantum efficiency, and this one is about a charge with a electrons with a, and hv, h is a Planck's constant, and v is nothing but a frequency. So we can say that c by lambda. Okay, so we can say that. That way we can write. Now, a short noise, that we say that it is a statistical nature or a statistical process, and that will generate the electron. Okay, that will generate the electron. By when it will generate the electron? When an optical signal that will be incident on the photo detector. And this process, it is about a statistical nature, or we can say that it is about a statistical process, and that statistical process may be called as a, or that statistical process follows a Poisson process, or may be called as a Poisson process. So that's why a short noise or a Poisson noise. Okay, so we'll say that it is about a short noise or a Poisson noise, and that why is we are saying, because a number of electrons or photons are generated, and they have some fluctuations. They have some fluctuations in number of whatever the number of generation of this particular electrons there, because that is nothing but a, when light falls on this, then electrons and protons are generated, but there will be a fluctuation in the generation of this electrons and photons, and that because of that fluctuations, then that will produce, or that will limit the sensitivity of the receiver. Now there is a fluctuations in the generation of photoelectron, and because of that fluctuation a current is generated, and that current is called as a short noise. That noise is called as short noise, or that current is called as a short noise current, and that short noise current has a mean square value in the receiver bandwidth, and that will be proportional to the average value of the photocurrent. So we can write I square short is equal to twice of Q, that is about IP, optical bandwidth E, M square, and F of M. That is M, that is for the multiplication factor for the avalanche photodiode, and F of M is about a figure of merit or a noise figure. Now that F of M, we say that it is about a noise figure, and this M is a multiplication factor for avalanche photodiode. Now these two terms that will be for the avalanche photodiode. If your pin diode is there, that M and M, F of M will be a 1. Only these terms are there. If it is a pin diode, only this term. If it is a APD avalanche photodiode, now these complete terms are there. So that is about a F of M is a noise figure that will be associated with the random nature of the avalanche process, and that is a factor for this. You can say it will be factor for this avalanche photodiode. And if you want to write the equations for this pin diode, only this will be the equation for the pin diode, and this complete term will be for the avalanche photodiode. That is about a short noise or a Poisson noise. We'll see next lecture, that will be a dark current and a dark bulk current and a that amplifier noise. We'll see thermal noise. We'll see in the next lecture.